Morning guys, I'd like to give you a lecture on Projectile Motion 2. So this is 7.8 in the book. So what we're going to be covering this morning is where else do we meet projectile motion aside from just the standard that we've been covering before. We're going to look at what would happen if we could switch gravity off. And we're going to look at how is projectile motion affected by air resistance, or air in general. So the first thing I'd like to talk about is essentially any motion where constant acceleration is in a different direction to its velocity will be projectile-like. So as long as you've got some acceleration acting in a different direction to the velocity, there'll be some projectile-like motion. I mean, the obvious counter example I think of is a braking car. I mean, if you think about the acceleration being in a off to one side, that kind of motion. So, I mean, if we look at the first example, figure 1 here, you can see that the initial direction is sort of that way, and then the acceleration is going to be kind of down the board. So you can see we've got a nice parabolic motion here. So rolling a ball across a board is one example of parabolic motion, or projectile-like motion, and the second example would be an electron beam deflection. So again, you've got the electrons going in that way, and they're being attracted downwards. So they're getting projectile-like motion. So there are two more examples of where you might see projectile motion, and then you can solve them with the Seevac equations, as long as we've got this very important constant acceleration in there. I'd like to talk very briefly about the different effects of air. Now, air can do one of two things really to an object moving through it. It can cause drag, and which slows you down, known as air resistance. Lots of physics problems say that air resistance is negligible. Which means you don't have to worry about it. The other thing air can do is cause lift. This is essentially how aeroplanes fly. So as they pass through the air, they'll have an upwards force generated just by passing through air. And very importantly, it all depends on the shape of the object to how much force of drag or of lift, or in the case of Formula 1 cars, of downwards lift, that we call downforce, is generated. So far I've covered where else would you meet projectile motion, and what would happen if you could switch gravity off. No, sorry, we haven't done that yet. And how is projectile motion affected by air resistance. We're now going to look at what would happen if we switched gravity off. Now, this diagram is a little bit complicated. I just want to kind of break down what's happening here. On the x-axis, we've got the horizontal position of the particle. So I'm just going to call that S horizontal. So S horizontal, and here we've got S vertical. And this u sine theta is the initial velocity in the vertical plane, and this initial velocity in the horizontal plane, this u cos theta. And kind of what they're saying is, well, what would the velocities look like if gravity was left off? Well, let's just have a quick look at that. Well, I'll just draw my Seevac table. So SUVANT, horizontal and vertical. So our initial velocity in the horizontal was u cos theta. And in the vertical was u sine theta. So what would the normal equations for S look like? Well, in the horizontal plane, it would, well, in either the equations would look like S equals ut plus a half at squared. If you've got a projectile, then gravity would be acting downward, so that equation would look a bit like S equals ut minus a half gt squared. Now, if we were to turn off gravity, this term would go to 0. So our distance would just be ut cos theta, and it would be here ut sine theta. So constant the whole time. So you can see why we end up with a straight line here if gravity was off, which is what we'd expect. Excuse me. Now, if we put gravity back on, that's what gives us this nice parabolic shape. Because if we look at the distance now in the vertical plane, we are going to get this minus a half gt squared added on. Don't forget that the acceleration in a horizontal sense is going to be 0 because gravity acts downwards and the velocity acts this way. So there will be no horizontal acceleration. So in summary, just quickly, what you need to know is that the distance in a vertical plane, in this case, is equal to ut sine theta, and then by putting gravity back on, we have this minus a half gt squared term here. And just to show you what the velocity looks like, well, v equals u plus at, right? So v would just equal u sine theta. Then by putting gravity back on, we have minus gt. So the terms in red are what we get if we put gravity back on. So now we've covered all three of the objectives for this lecture, but I'd just like to cover a quick worked example. So we've got an arrow is fired at a speed of 48 meters per second at an angle of 30 degrees above the horizontal from a height of 1.5 meters above level field. The arrow hits the target at the same height 0.25 seconds later. Calculate the maximum height above the field gained by the arrow. And we've got that old lovely saying in there, assume air resistance is negligible. So let's just draw a little diagram. So we've got a platform which is 1.5 meters above a level field, and it hits a target of the same height later, and it gets sent at an angle of 30 degrees, and it's fired at 48 meters per second, and it's asking what maximum height is. So let's work out the triangle first. Just double check it. So that's 30 and that's 48. So this is going to be 48 sine 30, 48 cos 30. So let's do our SUVATs in the horizontal plane and the vertical plane. So I might need a bit more space to write these actually. So, first of all, we know acceleration horizontally is 0, and we know the times are going to be the same. We know that if we have up as a positive direction, we know the vertical acceleration is minus g. What else do we know? Well, let's talk about a method of solving it. There's a couple of methods we can use. I'm going to use the method where we assume the first half of the motion is the same as the second half. So I'm going to say it takes 12.5 seconds to do half the motion. And at that point the final velocity will be 0 in a vertical sense. And the initial velocity will be 48 sine 30. And now we can have our pick of equations. I'm going to use v squared equals u squared plus 2as. So s equals v squared minus u squared over 2a. V is 0. So I've got minus, and that's 48 sine 30 squared over minus 2g. And obviously 2 minuses cancel out there, so 48 sine 30 squared over 2g. There you go, sorry about that. So the question that I was doing, work example on the book, page 135, is just wrong in the book. So I've decided to leave that one and do question 2 from the summary questions as an example. So the question is, an arrow hits the ground after being fired horizontally at 25 meters per second from the top of a tower 20 meters above ground. And we've got to calculate how long it takes to fall to the ground and the distance travelled horizontally. Now, key word in the question here, it's fired horizontally. So quick, very quick diagram. So platform 20 meters above the ground, and its velocity is 25 meters per second. So let's go ahead and write our SUVAT for that. So SUVAT and horizontal and vertical. Now straight away we know horizontal acceleration is always 0. Let's have positive up. Acceleration is going to be minus g. we've got, let's put our velocities in. Well, our horizontal velocity is going to be 25. Vertical velocity is 0. Let's look at our displacement. So it goes from the top to the bottom. So it's going to travel 20 meters downwards. So it's actually going to go minus 20. And what we've got to look at, we've got to try and find t. So we can now find t in the vertical plane. We haven't got v, so we can use s equals ut plus a half at squared to find t. Now we know u is 0. This is in the vertical plane, so we know u is 0. So we've got minus 20 equals minus a half gt squared. Negatives cancel, we've got 40 over g square root equals t. So I get the answer of 2.02 seconds, which I can go ahead and put in here. Now it's not exactly 2.02, so I'm going to keep the answer in my calculator and then use it as an exact value to find the distance travelled horizontally. Now we want to find s horizontally. So what can we do here? Well, we know u as an acceleration is going to be equal to v. So we can just use speed equals distance times time here. So we can have s equals u times t. So distance travelled horizontally is going to be 2.02 times 25. So 50.48. Now I check the significant figures in the question, so everything was given to 2, so I give my answer to 2, which is 50 meters. Okay guys, so today we have looked at where else we meet projectile motion. We've looked at what happens if you could switch gravity off, and we've looked at how is projectile motion affected by air resistance. So I hope you've learnt something today. Yeah, don't bother with that question. Page 135 that is. Okay guys, thank you very much.